All right, so now we have to solve. So you can do it multiple ways. Like I told you yesterday, I combine like terms. So I multiply there. So 13.8 times 60.7. So I got 837.66 times CP equals 856. Divide on both sides by 837.66. CP equals 856 divide 837.66, and I get 1.02 roughly joules over grams degrees Celsius. So when you look at your blue chart, which one did you decide it was? Magnesium? Okay, questions? Anybody have a question? All right, so from there, all right, number 3. What did you think based on what you found? Oh, you did it already?
I'm asking you, do you want like a copy or?
You just send it electronic. What you got for me?
I got the little hours on here, and so and then I have my personal statement on it.
No, I don't want that.
Okay.
Send me an email. Tell me what you've done over 4 years. If you work, what sports have you played? What have you done in 4 years?
Okay.
Okay? I mean, I don't need to know everything you've done over the course of 4 years, but something that tells me something about you outside of class. I can speak to your academics on the recommendation, but I need to make it sound like I know you much better than 1 semester on the recommendation in class.
Okay.
Okay? It sounds better if, I know you outside of school as opposed to just, 90 minutes in chemistry class. You get what I'm saying?
Yeah.
Okay, so
I'll send it to you.
that'd be great. That would be great. All right. So what's the difference between weight and mass? So nobody knows. Nobody looked it up. We're not going to calculate it. Not going to make you do that. Go ahead, Owen.
Weight's affected by gravity, while the amount of gravity while mass is affected by the amount of material in the object.
Okay. That speaks more to the definition that we talked about yesterday. I'm going to do something different. Anybody else got something? It's not necessarily wrong. I'm just looking for a different answer.
Weight is used while mass is used. No, I wouldn't say that.
That's a no.
Mass is the amount and weight's a measurement.
Mm-hmm.
I don't know how it's
Did anybody try to look up the answer? Y'all just making up stuff off the top of your heads.
I mean, I looked it up.
Go ahead, Owen.
Oh no, I said I did try to look at it.
Okay, I believe you. What were you going to say, Don? And you didn't what?
I just kept finding gravity stuff,
Just kept finding gravity stuff.
like what we talked about yesterday.
Okay, that makes sense. It's hard to decipher all this stuff on the internet. So I get it. All right, so let me tell you what the difference is in a way you can understand without all that junk from the internet. All right, so find your notes. Then we'll come back and talk about, don't let me forget what I put on the bottom of the opening. All right, because I will forget again. All right, so yesterday in our notes, we were on mass and weight, right? And I asked you the difference. All right, and Owen said weight has to do with gravity, and mass has to do with the amount of stuff, and that is correct. All right, now, let's say that we're here on Earth. And go to the moon. Can't write very well in that tiny little plane, or celestial body, rather. All right, so okay, so we're all standing on the Earth. If I go to the moon, what's going to happen? Why am I going to get lighter? Okay, I'm going way less. It's a great place to go for Miss Wall, okay? So I'm going to weigh less. And y'all can all tell me because there's less gravity. That's very good. Now, tell me about my mass,
Stays the same.
okay? Now, can you tell me the difference between mass and weight?
Weight changes with gravity and mass stays the same.
Okay, so weight changes with what? There's a word that I'm looking for. It's an L word. Okay. Let me see. I don't have a lot of space here. What happens if I go here? Okay. What happens to my mass? Okay. Okay. So, what's the relationship? Can you fill in my blank line?
So it starts with an L.
Can you give us the next one?
Y'all are like playing, huh?
Location.
Mhm.
Oh, seriously? Dang.
What?
Weight changes with location. I told you I don't shoot people for wrong answers. Okay, I'm a pacifist. Most days. Some days I'm not. Most days I'm a pacifist. All right, weight changes with location. Mass stays the same. So the only way to change your mass is to do what to you?
Add more.
Yeah, so if I chop off your arm, I can change your mass. Short of that, your mass is not going to change, okay? Gravity changes your weight because the force that something pulls on you changes your weight, all right? Gravity at the moon, I need to take that down, is roughly 1/5 that of the Earth, okay? So if you take what you know your weight is and you divide it by 5, you will come up with your approximate weight on the moon. Now, Jupiter, I'd have to look it up. I think it's around 20 times that of the Earth, but I can't swear to that. So there's no way I'm ever going to Jupiter. So, huh?
You even walk like giant.
I have no idea. Now, the other thing that I forgot yesterday. All right, we've calculated with specific heat, but I forgot to tell you what specific heat is for. All right, what does, and I don't know if you want to squeeze this in back where it went or if you just want to add it, okay? What does specific heat mean? Or what does specific heat tell us? I forgot that yesterday when we were calculating, and it doesn't make sense to calculate with specific heat and you guys not know what these numbers are for, okay? I'm not going to define specific, well, I guess I could, all right? All right, first of all, the definition for specific heat is the amount of energy needed to raise the temperature of 1 gram of material 1 degree Celsius. Now, you're never going to have me ask you to write down or memorize the definition just for the purpose of writing down the definition, okay? I'm more about what does the definition mean or tell us, okay? I don't ever give you vocabulary lists and ask you to write down vocabulary words simply because I don't teach vocabulary that way. I want you to know what the purpose of specific heat is and what it tells us and why we use specific heat. All right, we've already learned to calculate with specific heat, but even though we've calculated with specific heat, for most of you, those numbers mean absolutely nothing other than being able to plug them into the equation. So, we're going to talk about what the numbers mean in a way that you guys can use them to understand. So, to explain specific heat, I'm going to give you, I'll give you 3 numbers, but 2 of them are the ones I want to be able to use because most of you can relate to these. All right, water has a specific heat of 4.184 joules over grams degrees Celsius. Aluminum, I think it's 0.897, but I'll double check that just to make sure I'm right. Because again, I told you, getting older, a little more forgetful of my old age. Yep. And let's pick one that you can, what other one would y'all probably have at home? I'll use gold. Y'all probably wouldn't do anything with it, or not this, but it's one y'all can relate to. All right, so those are all things that you guys are familiar with and have. Now, for the purposes of this discussion, this would be considered a large specific heat. These 2 are small specific heats. Okay? So, what is the difference between a large specific heat and a small specific heat? All right? We're going to talk about aluminum foil for just a second because I put aluminum up there because most people can relate to aluminum, particularly if you guys have ever used aluminum to cook with at all. Has anybody ever used aluminum to cook with? I'm the person who does the lion's share of the cooking in my house, or I did until 7 weeks ago when I fell off a sidewalk. Now I do almost no cooking. I stand in the kitchen and give directions. My children cannot wait for me to be able to cook again because they're sick of being mini slaves. I kid you not, by the way. All right. If you don't think so, have the primary person in your house not be able to cook and you have to do all the cooking, and you'll be tired of them too. I can't tie my shoes, people. So every morning I get up and my daughter has to tie my shoes. So imagine that. I can't put my watch on without help. The list of things I can't do without aid would shock y'all. So when we talk about aluminum foil, okay? All right, tell me what we know about aluminum foil. If we put aluminum foil around, let's just say we're making spaghetti and we want some warm bread to go with our spaghetti. All right, we wrap the bread in aluminum, stick it in the oven. We let it heat, let's just say 10 minutes. Got to get it out of the oven. How soon does the foil cool when we pull it away from the bread? Does it take a long time or is it quick? It's very quick, okay? Aluminum foil heats and cools very quickly, okay? Now, things that heat and cool quickly have small specific heats. Now, anything with a small specific heat is going to be like aluminum foil. So if you have gold, which had a 0.129 specific heat, it's going to heat and cool even faster. Okay? Now, one of the nice things about aluminum foil, one of the reasons we use it, aside from the fact it's cheap and easy to manufacture, is it does heat and cool very quickly. My children are odd. They do not like grill marks on their food. So when we grill on the grill, I have to put down aluminum foil. So every time I finish grilling, I have to pull the aluminum foil off the grill. How hard is it for me to pull the aluminum foil off the grill? Really? Thought I just tell you about the foil.
That's easy.
Not hard. It's easy. All I got to do is grab it with my fingertips and pull the foil off. Now, if it's got grease and goo all over the end of it, can I do that? No, but as long as the foil is not greasy on the end, I can grab it with my fingers and pull it off. and then I just throw it in the trash can. Now, if it's got stuff on it that's burnt on or gross, then I can't because clearly it's not just the full. But if it's just the full, then I can pull it away pretty easily. Now, water, on the other hand, what can we say about water? Does water cool quickly, or does it take a long time? It takes a long time, okay? Water heats and cools very slowly, okay? Because it heats and cools very slowly, all right, they have very large specific heats. So, for those of you who remember your earth science, hurricane season goes from when to when?
August or something to April.
August.
I don't know.
I know September.
Yes, it is. June the 1st through
September.
a little later,
October.
a little later,
November.
November the 30th. Okay? Now, for a lot of you, by November the 30th, you're wearing what? Sweaters, pants, sweatshirts. Some of y'all will be in winter coats. All right? The reason that hurricane season lasts that long is water stays warm enough to be able to support a hurricane all the way through the end of November. For some of you, if you went to the beach in October, you would still be able to walk along the beach and probably put your feet in the water because the water is warm enough to be able to do that. Okay? Water heats slowly. So once it gets warm, it stays warm for a long period of time. The air temperature will cool quickly, but the water temperature will not. Now, spring break. We go, let's just say it's late March, early April. We go to the beach, it might be 75, 80, 85 degrees. We put our feet in the water, how's the water feel? It's freezing, okay? Because the air temperature has gotten warmer. Has the ocean temperature caught up with the air temperature? No, it takes a long time for the sun to beat down on that water and finally get it to heat up, okay? If any of you join pools and go to the pool Memorial Day weekend, how's the water feel? Anybody ever done that? If you do, it's cold that first weekend. The pool just gets filled right before Memorial Day weekend. That water's cold. It needs the sun to beat down on it and start warming it up. After a couple weeks, though, it'll be nice and toasty. Water heats very, very slowly. These things heat quickly. So things that heat quickly have low or small specific heats. Things that heat very, very slowly have large specific heats. Does that make sense? You got it? Okay. Now, we want to talk about where we were yesterday and maybe get started on the lab that I set up at the back of the room. If we don't get to it today, then we're going to finish it and do it tomorrow. Okay? Now, we were going to talk about physical and chemical properties yesterday, and we're going to do those today, and physical and chemical change. So, depending on your middle school background and experience, you may have already had everything I'm getting ready to do today. If you had a really good experience, you may have had it. Those of you who had the subs, I apologize that you had a sub A. And B, you probably had none of this, and I'm sincerely sorry, okay? So we're going to start with physical properties, and then we'll do chemical, and then we'll bounce into change. They're very, very similar. For those of you who, after we do the properties, you're like, dang, I can't tell the difference between these two, Ms. Wall. When we do the 5 indicators of chemical change, it'll sort of solidify that for you guys and make it a lot easier to figure it out. All right, but we're going to start with physical properties. All right, so a physical property is a property that can be identified without altering the identity spelled wrong. I think I told you I spelled terrible too. I-D-E-N-T. Spell it for me. I got it wrong. I-T-Y. Thank you. Of, whoops. Oh, I got a little out of hand there. property that can be identified without altering the identity of a material. Okay? Now, to help figure out some physical properties. I want y'all to look at just my big lab desk that's at the front of the room. Don't consider the stuff that's stacked on the desk, okay? Just the physical desk itself. What things could you use to describe the desk? Okay, so the material is made of, so material / composition. Okay, give me something else.
Round.
What's round?
Is it round?
Oh, brown. Oh, color. Okay. Size. Can you be more specific in how you would measure the size? Yes, you can. Give me some things like volume. Give me something else. Mass. There you go. That's what I'm looking for, Diamond. So volume, mass. What else?
Density?
Sure. Okay. There are lots of things y'all can give me about this desk.
Angular.
Sure. Shape. Something else. Sure. Hardness. When y'all talked about not physical science, sorry, earth science with rocks, y'all talked about hardness, should have talked about the Mohs scale. All right. Hardness in chemistry also applies. Some elements are very soft, some are very hard. What things did you measure last week?
Area?
Sure. What do you need to calculate area?
Flat. Smooth.
Got any others? All those are physical properties. Okay? Calculated one last night. Which ones?
Heat.
Needs another word. Yep. Specific heat. For temperature, it needs something in front of it. Look at your blue sheets on the front page.
Standard temperature.
Melting point. Okay. There's another one that's opposite of that if you remember it. Freezing point. And there's one that's similar to that, but it's not an opposite. All right, that's good enough for the time being. Okay, all of those are physical properties. Now, from there, during the lab, you're going to have to label these as intensive and extensive. Now, only physical properties are intensive and extensive. So in a minute, when we talk about chemical properties, am I going to label them intensive and extensive? No. Okay, because the list is going to be much, much shorter. Okay, and we're not going to label them intensive and extensive. Only physical properties are intensive and extensive. All right, so what does it mean to be intensive? Intensive means it does not depend on size. Okay? Number 2. Extensive means it does depend on size or amount. Intensive does not depend on size or amount, and extensive does depend on size or amount. All right, we're there? Ready to wait? Where are we at? All right, so if I cruise back for a second. All right, I'll take blue. All right, for example, color. Let's say that I take Alex's lovely pink, because that's nice and bright today, and I cut it into 4 squares. Will I have altered his color of hoodie?
No.
That is an intensive property because color will not change. Okay? Now, it has a mass, right? If I cut it into 4 squares and throw it in this corner, that corner, that corner, and that corner, will I have altered its mass?
Yes.
Yes, because now it will only weigh a what when I put it on the scale? A 1/4, because now I will not have the same amount. So mass is extensive. Its mass will no longer be the same because I've separated it into 4 sections. Okay? So what can we say about the remaining things that I have up there? If I cut my desk in half, will its composition change? No, it's still going to be made out of the same stuff. So its composition is intensive. Will its volume change? If I haul half of it over there to Ms. Rector and I leave half of it here, will its volume have changed? Then it's extensive. Will its specific heat change? Here or no? What about the rest of y'all? I got a no from Owen, and I got some nods of yes. At least Dalmatia's nodding at me because some of the rest of y'all look dead. You got your blue charts? Look on the first page. What you see in the first column? That first column down there at the bottom. What's it say? Under metal. First column beside metal. It says specific heat. What's the specific heat of gold? Does it ever change? No. Because you can look it up on that chart. Specific heat does not change. So is it intensive or extensive? It's intensive. It doesn't change. All right. What about the freezing point? It's intensive. What do you know the freezing point of water is?
32.
That's on what scale? Fahrenheit. What is it on Celsius? 0. Okay.
Doesn't the specific heat change when there's less of the material because it's faster? Than
Nope. Doesn't change.
so what does change when there's less of it?
Time.
No.
The amount of time it takes for it to happen. All right. Boiling point. Same thing here. So, for example, you want water to boil, it will still boil at 100 degrees Celsius or 212 Fahrenheit. but it will take less time if you have a smaller amount versus a bigger amount. That's the only thing that changes is the amount of time. It still boils at 100 degrees Celsius. All right, what about density? Who didn't do the lab for me? It's just Angel, wasn't it? Go outside for a minute. Go answer a question from the lab. I'll try to talk quietly. That's really hard for me, though. This is the question we all got wrong on the lab.
Yeah.
Intensive. The density of the block of the wood. If I went around and gathered y'all's lab papers, almost every single one of y'all have 0.54, 0.52, 0.56, 0.51, 0.50, 0.49. Do you see a pattern? What's the density of the block of wood? Was the density different? Why was the density not different? It's the what? It's the same material. That's a 1x12 block of wood that I had my husband cut in 2-inch and 4-inch sections. Okay? It's the same material. That's all you had to put for number 2. Y'all put all this crap down about the mass and the length and the width and the height. It's the same block of wood, people. That's all you had to write. It's the same material. Okay? It's intensive. That was it. Okay, you can let Angel back in. Angel! It was easier than walking. All right, shape. I just want to tell them the answer on the line. So, shape. Shape is usually going to be extensive. Now, when we talk about it later in the semester and we talk about the geometric shape on a molecular level, we'll change that answer. But for right now, because you only know this kind of shape, we'll leave it as extensive. Hardness. That's intensive. All right, melting point. Texture. Yep. Area. That's extensive. Area will change if we cut the desk in half. Length. Width. Height. And width. Oh, sorry. Wait. I can't read my own handwriting. Yes. Most of the things you're going to largely measure the way we did last week, those things are going to be extensive. Most of the things that come off your blue sheet, like melting point, boiling point, density, specific heat, those things are going to be intensive. Everybody okay with those? All right. So chemical properties. What are chemical properties? Chemical properties can be observed but will, and I'm shortening this, the identity of a material. Okay? These will alter the identity of a material. Now, this list is going to be much shorter. Things that you might know are chemical changes are things like being flammable. Because you know, if you burn something, you can't get that back. Okay? It's going to turn into ash, and it's going to have altered the original identity of the material. All right? Decomposing is going to be a chemical property. Able to oxidize, which is a nice fancy word for what? Being able to rust. Let's see, what else do I want to put up there? Able to combust.
Like blow up entirely or just break apart?
Combust would be to explode. Let's see if I put anything else down. I'm having a senior moment that you would recognize. I think I put neutralize up there. That one you would recognize. By neutralize, I'm thinking acid base. For example, any of you, hopefully not at your age, have to take any type of acid reflux medicine, Tums, anything like that. Yeah, I got Karina nodding at me back there. Mostly, I would hope it would be your parents who would have to take any type of acid reflux or heartburn medicine, but that would also work there. But those would be examples of things that would be chemical property type words. Now, can I label any of these as intensive or extensive?
No.
No, I cannot. All right. If you saw the word react anywhere, react would also fit as a chemical property, but I'm not going to put that word up there at the moment because it just looks weird. All right. Now, the holes are on the wrong side of this worksheet. The person who helped me put the holes on the back side first. All right, so by the time Angel gets around to that side, this side will probably be done with the worksheet. This is so fast on the front side. So on the table side, I just want you to put a check box under chemical or physical. There are a few on this that we did not label as chemical or physical, and I wasn't going to go through and try to get you to figure out every single chemical or physical property we could come up with. So I'm giving this to you to see if we can label a few more. Okay? Let's do the front side. And then we're going to talk about the indicators of chemical change. And that will help a lot of us figure it out. Right there.
If it says odor, does it mean it produces an odor or it just has one?
Just has one. Got it done? All right, so what do we think about, I have one here. Number one, blue color. Physical, density, flammability, solubility. All right, that's usually one that causes some discussion. What does it mean to be soluble? To dissolve. So if it dissolves, what do we think? It doesn't change, it's physical, okay? When you dissolve sugar in water, it still tastes sweet. It still has all the same properties as being sugar. Now, there's one notable exception to that, and that's Alka-Seltzer. And will remind me, and I'll talk about Alka-Seltzer when we do the 5 indicators, okay? And those of you who have ever seen Alka-Seltzer dissolve, you will know why when we do the 5 indicators, all right? Reacts with acid to form hydrogen. Supports combustion. Sour taste. That is physical. Taste is a physical property. Some things just taste sour. All right, melting point. Physical. reacts with the water to form a gas. It's chemical, reacts with the base to form water. Hardness, boiling point, can neutralize the base. Luster, that's physical. Everybody remembers that as shiny, right? Okay. Most middle school teachers have covered that by the time y'all get to me. And odor, that's physical. Some things just naturally smell bad, and that's just a physical property. Okay? All right, now let's talk about the last piece so that we can do the lab today, I hope. Now, we won't be able to finish it today, but we should be able to at least do half of it, I think. All right, so physical change. Now, physical change, all right, will not alter identity, first of all, which we've already talked about. All right, but the key here to being a physical change is you will not get a new material with new properties. Okay, and when we talk about chemical in just a second, you will get a new material and you will get new properties. So, if we're not going to get a new material and we're not going to get new properties, what kind of things are going to fall under physical change? How do we get physical changes? Well, the standard things that you probably learned about in middle school, if you did this, would have been like you could cut something, you could grind, you could tear, okay? You could do any of those things. If you could beat the fool out of it, cut it up, grind it up, puree it, you could physically change it. But the biggest part that always causes issues for students under physical change are state changes, okay? State changes are usually where students get hung up under physical and chemical change, okay? So what are the state changes that fall under physical changes? Can anybody give me a state change? Like water to a gas. What's a water changes to a gas called? Okay, so when we evaporate something, that is a state change. It's still water, okay? You start as liquid water, and you become gaseous water, okay? Which is more affectionately known as steam. But it's still water, so it's a state change. So we could evaporate, we can condense or condensate, condensation, any of those variations on the word condensation. Now, evaporate and condensation are the opposites to each other. So can you give me any other words for state changes? Think of any other state changes you might have learned. No, that's a biology word. Freeze. What's the opposite of freeze? All right. Boiling is not the opposite. Melt is the opposite. Now, boil is certainly a word we can put up here that's a phase change. And we will talk about the difference between boiling and evaporation because they are different from one another. And you'll have to learn the differences between those. All right. So we've got most of them. Does anybody remember the one that starts with an S? I thought I heard it. The one that starts with an S. The phase change that starts with an S. Denasia's on what? Y'all are in the ballpark. Sublimation. The last one is called deposition. And I would have been truly impressed if anybody knew that one. All right, we'll talk about all 6 of those before Christmas when we're all dying to go home for Christmas break. It's in that really, really boring unit I told you about. Okay? The phase changes are god-awful. There's nothing I can do to make it better. There is math that goes with it, though. All right, you have to learn how to calculate the amount of energy used to make those phase changes and read them off the graph. Elijah's looking at me like, dear God, please spare me. It's a really hot topic. Okay, so those are chemical change or physical changes. So most people look at that and go, "I'm not supposed to know that's a physical change. That doesn't make any sense to me. I can't tell if something's sublimating." That's true. Most people have absolutely no idea if something's sublimating. So how can we figure it out? Well, the nice part about this is with a chemical change, I can give you 5 things to look for. Okay? A chemical change, first of all, will alter the identity. You will get a new material with all new properties. So to illustrate this, we're going to talk about something that most of us use every day. Can anybody tell me what NaCl is?
So,
All right, plain old table salt. Tell me what table salt looks like.
Oh, wait.
Okay, it's a white crystal. And I'm just going to write it safe to eat. Now, when I write safe to eat, I'm saying we can have it on our lunch today and nobody's going to drop dead. I'm not telling you can eat the salt shaker every day for 25 years.
Teachers, at this time, we ask that if you have a 10th grade classroom, that you accompany those students to the auditorium. If you do not have a 10th grade classroom but have 10th graders in your class, please send them to the auditorium at this time. Please enter the auditorium quietly. Thank
Those of you who are missing, the video will be on YouTube, so by all means, catch up this evening. All right, so when you look at this, Na plus Cl2. That's all sophomores I have, really? Oh, so far we had more than that. So, Na. Na is a what? Anybody know? It is sodium. All right, it's a metal. Okay? Sodium is a silver metal. It explodes in water. Okay? So, we're taking a silver metal. All right, it's in group 1. It explodes in water. We're going to combine it with chlorine. This is a yellow, poisonous gas. Okay, a little sniff of chlorine gas, whoop, drop dead. All right, we've got a metal that is explosive in water with a gas that you sniff a little bit of, drop dead. Okay, combine the two, and suddenly they're safe to eat. We can sprinkle it on our lunch today, and no one will die. All right. It undergoes a chemical change. It's completely safe to eat. All right? Now, how do we know that it underwent a chemical change? It doesn't kill us, so that's important. But I'm going to tell you which indicator it has in just a second. Okay? Now, that's what I'm talking about when I say it gets all new properties. It does not keep any of what it started with. It gets all brand new properties. These properties that it started with go away completely. Does that make sense? Now, back here with physical properties, do all of its properties go away? No. The properties it started with, it keeps. It might change states, but it doesn't go away. Last night we had onions at my house for dinner. Did all the properties of the onion go away when we finished with them? No. When we put the onions in the food and we cooked them, were all the properties of the onion gone when we finished cooking the food? No, those onion properties were still there. Okay? With chemical properties, If I had done that, would the onion properties be gone? Yes. Okay. So how do we know which change we had? We have 5 indicators we're going to look for in this lab. There are 5 indicators of chemical change. And you have to see how many to know you have it. How many do you think you have to see? 1. All you got to have is 1. Okay? Number 1, the production of light. If you produce a big burst of bright light, you were a chemical change. Okay? Now, that example I just gave you with the sodium and the chlorine gas to make salt, right here, makes light. Nice big bright burst of light. That's not how we make salt, by the way, but it will work that way. All right, number 2, and I will give you a hint when you're doing the lab and you're answering the questions, you're going to see all 5 of these. Number 2, production of a gas. How are you going to know you had a gas in the lab? Most gases are colorless and odorless. There you go. Most of the time, you're going to see bubbles. Most of the time. For example, carbon dioxide or carbon monoxide is the silent deadly killer. Carbon dioxide can't smell either. Most people, when people pass gas, y'all are all like, dang, you stink. Methane is also odorless. All right? It's the other stuff that comes out with y'all that smells so bad. Just saying. All right, number 3. Let me change colors there. Number 3, change in color. Now, I need to preface this by saying it must be an unexpected color change. For example, if you go to Food Line and buy grape Kool-Aid and put grape Kool-Aid in water and it turns purple, that is not a color change. That is purple Kool-Aid dye you put in water and it's going to turn purple. If you buy strawberry and it turns red, that is not a color change. If you mix 2 clear liquids and it turns bright green, that's a color change. That's a chemical change. Okay? If you mix pink and clear and it turns pink, that is not a color change. But if you mix pink and clear and it turns bright blue, that's a color change. Okay? Unexpected color change. Now, sometimes when I ask about the color of leaves changing in the fall, people go, oh, that's not a color change this fall. That's expected. We know the leaves are going to change colors. Hold the phone, people. Now, y'all took biology. Y'all know what's supposed to happen with the leaves in the fall, right? Y'all know the whole process in leaves is a biological chemical change, right? Just because we all know that leaves are going to change colors in the fall does not mean that that process is now not an unexpected color change, okay? We know that, but the process in the leaves is a what process? That's a chemical change, even though we know what's going to happen, okay? So leaves changing colors is a chemical process, even though we know that's going to happen. Okay? So don't let that get you. All right, number 4 and number 5. Number 4 is change in temperature. Now, there's 2 temperature changes that usually you guys know when you come to me. So let's see if you do. They start with E's. Anybody remember the names for the temperature changes that you might have learned in biology class that start with E's? Not external. Huh? I'll give you Diamond's method. I'll give you the second letter. How about the third letter?
Endothermic and exothermic.
There you go. Exothermic and endothermic. Now, y'all remember what the words mean?
Exothermic.
Both of them are heat. What happens to the heat is what I want to know.
Heat goes.
One gives off and one is absorbed. Which one gives off the heat?
Exothermic.
Okay, exothermic, heat is released. Endo, heat is absorbed. All right, now for how it's going to feel in the lab, because you're going to need to feel some things to know if you had endo or exothermic. Okay, there's a bag and a test tube. So one you're going to have to feel, you're actually going to feel both. Nothing's going to burn you, so don't worry about being burnt. I'm not going to give anybody anything that's going to hurt you. So how are you going to know if it's endothermic? It's going to feel how? That's right. Very good, Anthony. All right, this one will feel warm or hot. It's not really going to feel hot. It'll just feel warm. All right, so that means endothermic will feel how? It'll feel cool. All right, so the last thing you're looking for is the formation of a precipitate. Now, when I say precipitate in chemistry class, I am not talking about rain, sleet, snow, or any of those other things that fall from the sky. Okay? A precipitate in chemistry class is a solid. Right? It's a solid formed from two liquids. Precipitate is a solid formed from two liquids. Okay? So, if I asked you if making Kool-Aid is a physical or a chemical change, in your head, run through the 5 indicators. Everybody here has made Kool-Aid at some point, even if you don't like Kool-Aid. Did you form light? Nope. Did you produce a gas? Did you see bubbles? Did you change colors that was unexpected? Did you change the temperature? But when I say change the temperature, I mean, did it get hot or cold when you mixed the water with the Kool-Aid packet? Did it start to get hot or cold when you mixed them on its own? No. And did you form a solid at the bottom when you mix the stuff together? So was it a chemical change? No. All you got to do is run through those 5 things. If you didn't see any of those 5 things, it's automatically what kind of change? Physical. Okay? You got to have one of the 5 to be a chemical change. If you don't have one of the 5, it's a what? It's a physical change. All right, flip your paper over to the back side. We're going to see if we can figure out if things are physical or chemical. I gave you a minute ago. So, if we look at the first description, all right, I want to do 2 things. Number 1, this one's an easy one. Sodium hydroxide dissolves in water. It's physical, it just dissolves. All right, number 2, hydrochloric acid reacts with potassium hydroxide to produce the salt water and heat. All right, why is it chemical? All right, so it's chemical, and I want you to tell me the indicator. So you can just write out to the side heat. Okay? But I want you to be able to tell me why it's chemical when I ask you. Okay? So I want you to run through the other 17, or 15 really, real quick. So, and you can just write P or C. You don't have to write out the words to make it faster. And then know why it's chemical when I ask you. Because if you tell me it's chemical, I want to know which indicator. Y'all done? Any more time? Where we at?
Miss Wall,
Yes, ma'am.
can you send Antoinette Winters to the office signing out?
I will.
Thank you.
Welcome. All right, number one. Oh, number three. We did one and two. So, what do you think about a pellet of sodium to slice in two? All right, number four. Water is heated and changed to steam. Physical. Number five. Potassium chlorate decomposes. Why'd you say that one? Okay, what indicator do you see? It produces a gas. Okay. Iron rust. What indicator? Okay, out of those five, which one do you see? What? Color change. Okay. Rusting is color change. All right. When placed in water, a sodium pellet catches on fire as hydrogen gas is liberated and sodium hydroxide forms. So, it is chemical. What indicator do you see? All right. Heat is released is one. What else? All right. That would be the heat is released is exothermic. That's good. That's the same one. What? Produces light, and there's one more. Gas. There was three of them listed there. Okay, there was three different indicators in that one. All right, so the next would be evaporation. That was physical. Ice melting. All right, 10 always causes issues. Milk souring. It is chemical. All right, why? It will actually precipitate, and it will also do one other. That's the solid. It will solidify. And there's one more. Anybody ever seen sour milk? That's the precipitate. It will also do one more. It will change color if you leave it long enough. If you've ever left it long enough to see gas, I don't want to see it. I've never left it that long. I have seen it precipitate and color change. All right. Sugar dissolves in water. That's physical. Wood rotting. This one has more than one. It is chemical. What indicators do we see? You will probably see color change. There's another one that's pretty obvious, I think. See it a lot in the wintertime. Which one do you think you'd see up there in the wintertime? It comes off the pile of wood. It's cold outside. Heat is released. You're going to see the heat coming off of it. Heat's given off. Usually you see steam coming off of it. Y'all have never seen a pile of compost and seen all the steam coming off the top of wood with this rotting? Y'all need to get out more.
I've seen things high. Big pile of trash.
Same concept, except wood in the wintertime, and you see steam coming off the wood.
I've never seen them. Unless it's like fresh trash.
Okay, we need to expand your area of where you hang out, Joe. All right. Now, number 13 is going to be lost on most of you unless you've ever cooked pancakes. Have you cooked pancakes? Have you seen it? Okay. So pancakes cooking on a griddle. All right. One of those is obviously right. Which one? It is chemical. Why?
Yes.
That's right. Because you see what in the pancakes?
Bubbles.
Bubbles. Why I asked that? If you've never seen it, you don't know. All right. Number 14. Your biology teachers are going to be disappointed if you don't get this right. You just crushed them.
Chemical.
Why is it chemical? Which is called, yes. All that grass has to go through photosynthesis to grow, people. A tire is inflated with air. Yes. Food is digested in the stomach. Now, which indicators can y'all label for me? Yes. Even though most of us wouldn't admit we have it. What else? Yes, that would be gas. So you got the bubbles. What else? Color change. One more. Yes. Those are 3 we should all have. All right, water is absorbed by a paper towel. Yes. All right. All right, what do I got time-wise? We got 10 minutes. I ain't sure we got time to get up and do that. We may have to table that for tomorrow. Here, let's work on our review for the test. And we'll do the lab tomorrow, first thing, after the opening. All right. We're going to work on the lab first thing after the opening tomorrow instead of chopping it up. It'll just work better. So, we're going to look at the paper that I'm going to give you for review for the test. I have one on significant digits that I haven't given you, and I'll give that to you tomorrow for those people who want it. But a lot of you did fabulous on the quiz, so if you don't want it, you don't have to have it. I just keep it reserved in case people need it. I don't think anybody failed the quiz. I think 70 or 60 was what we have, so everybody passed. So if you want it, you can have it. This is the one that we need to make sure we can do. Because there are some areas on the test that if I don't go over, some of us will struggle with, and I don't want it to cost points. Angels, nice way. All right, thank you, my dear. All right, 1 through 6 is very self-explanatory. Jump down to numbers 7 through 11. Those are the ones I want to focus on in our 10 minutes through 11. So look at number 7. You will see questions like 7 through 11 on the test. All right, tell me what's weird or squirrely about question number 7 and why people are going to get it wrong on the test. Because even though we're going over this, people are still going to get it wrong on the test. Okay? I heard somebody over here say it. Put in SI units. What do I mean in that question? What am I asking you to do in that question when I say put it in SI units? What am I asking for? No. Per. All right. I want the answer in kilograms per meter cubed. So I'm asking for 2 things in this question. I'm asking A, do you know the SI units? And B, can you convert them? And really C, can you then find density in the right SI units? Okay? So I'm getting more bang for my buck in one question. So, in the question, did I give you the mass in kilograms? So what do you have to do? So you have to take the grams, which I gave you in 48.6 grams. You guys have to change those to kilograms. Then I gave you 4.58 milliliters, and you have to change those to what? Centimeters cubed. And then from centimeters cubed into what? Meters cubed. Once you have that, then you can plug it into what? Then you can do your density equals mass over volume. Okay? You have to do all of that first to then solve. You understand what I'm asking for? Yeah, that's a normal test question tomorrow. Or Friday. Sorry, Friday. Not Thursday yet. I'm ahead of myself. Elijah's looking at me like this lady's nuts. Jada's just telling me point blank, I'm going to fail. They're not all this hard on the test, just this one. All right, so that's number 7. Tell me what's weird about number 8. What's weird about number 8? 2 different measurements. One is in deciliters and one's in what? Milliliters. So what are we going to need to do that deciliters? Change it to milliliters. So you've got 12.8 grams per milliliter, and you need to take that 7.3 deciliter and change deciliter into what? Change it to milliliters. And then you can plug it in your formula. All right, I want you to work on 7 through 11 right now, okay? And if you don't finish, which you're not going to finish 7 through 11, I want you to do 7 through 11 for homework, okay? Don't worry about 1 through 6. 7 through 11. That's what I want you to focus on right now.